All right, section 3.5, we're going to be taking a look at limits at infinity. And as we take a look at this, I first want to define by what we mean by that, because there's a couple different things you could kind of go with in terms of that phrase. So what we're going to mean is the following. So limits at infinity, let L be a real number. The statement, the limit as x approaches infinity of f of x equals L, means that for each epsilon greater than 0, there exists an m such that f of x minus L is less than epsilon whenever x is less than m. And we have a similar statement on the second line, talking about what happens when we are on the negative side of the axis, basically. So what we're looking at is we're looking at what happens to graphs on the edges. Another way to describe it is called end behavior. So if that phrase is helpful to you, jot that down. This is talking about end behavior of graphs. What happens to the far left and what happens to the, happens to the far right and happens to the far left. You encounter this idea in college algebra. When you encounter it in college algebra, you encounter it specifically for functions called rational functions. It's places where the numerator and the denominator's degrees have certain properties. If the degree on the top is less, then there's one thing that happens. If the degree on top is greater, there's another thing that happens. And if the degrees are the same, there's a third condition that can happen. And when you look at them in that light, you're always talking about what are called horizontal asymptotes. So if we have a line y equal L, it is a horizontal asymptote of the graph if the graph is approaching that constant value. And the picture you might have in mind, again from college algebra, might look something like this. And I'll draw it in dotted just to be real clear. So from this side, it looks like this, or maybe from the left side, it looks like this. So it's sort of leveling off at that dotted line, and that dotted line in our definition is what we're calling L. Shake your head if that looks like something you've seen before. Okay, good. So we're going to be approaching this from a slightly different perspective because, of course, we're thinking about this from calculus, but everything you did in college algebra is still applicable. It's still correct. We're just going to expand what we're looking at in terms of our functions. We're not limited now just to rational functions, which we were before. However, rational functions will come about quite frequently because horizontal asymptotes do happen for asymptotes or for functions that are in rational form. So we're going to take an example, and we're going to do this example with 3 different denominators, I believe. So, one more thing about limits at infinity, I guess. Sorry, I was jumping ahead to the example. All right, so this is specifically for rational functions. So if r is a positive rational number and c is any real number, then the limit as x approaches infinity of c over x to the r is equal to 0. Okay, r is positive and rational. Furthermore, if x to the r is defined when x is less than 0, then the limit as x goes to negative infinity of c over x to the r is also 0. And the picture you might have in mind, in fact, the function you might have in mind might look something like this. The real simple one, like 1 over x. All right, so the exponent is a very unexciting 1 here. That's both positive and rational. And if you were to graph this, it actually, well, let me change that back, has the graphs that look something like this. I think I flipped it upside down. In fact, I'm sure of it. All right, let's go like this. So on the end points of this graph, we're approaching the x-axis. That's the limit 0. Okay? And this is telling you that it doesn't matter what the value is up here where I put my 1, as long as it's positive and as long as it's rational, right? So rational numbers, fractions, decimals, all the good stuff, that you've seen before, even, 0, well, yeah, because it says positive and rational. We don't want to use 0, sorry. So anything, even like 0.5, I guess I could use that. Right, so it's still positive and it's still rational, but it's even smaller than 1 would work, and it would have this same feature. And it does specifically say as long as the second part, as long as x to the r is defined. So what that's talking about is, like, imagine, for example, that you did have x to the 1/2. So if you had 1 over x to the 1/2, 1/2 is actually the same as the fraction that would look like that, right? The rational denominator would be the square root of x. And so in that case, I can't talk about the negative side because I can't have negative numbers underneath it. So that's what that condition at the bottom is referring to, is that there are locations where you can't have negative inputs for x. But if you can, then we get the left-hand side of this graph tending towards 0 as well. Okay, so we're going to take a look at some different functions. And we will go back in our minds and think about, okay, well, what happens if I think about this from a different perspective, all right? Basically, the perspective of algebra. So here's our function. We have f of x equals 5x cubed minus 3x squared plus 10x. And on part A, we're taking that expression and we're dividing it by x squared. So the first thing we're going to do is we're going to actually write it out. So this is 5x cubed minus 3x squared plus 10x over x squared. Okay, so we're not going to spend a lot of time talking about what we learned in college algebra, but let me just make a comment right here to notice that right here, your degree of your numerator is 3 and the degree of the denominator is 2, right? So in college algebra, what we actually saw happen in this case is that there wasn't a horizontal asymptote, and there was something called a slant or an oblique asymptote. And if you don't remember all the details about that, that's totally fine. But if you do, that's what the kind of function is that we're looking at here. Okay? So what we're going to be considering as we look at this is some of the things that we have done before in terms of algebra simplification. Since I have x squared in the denominator, I can divide each piece of the numerator by that single termed x squared. So that means that the 5x cubed divided by the x squared would give me 5x, right? And then the negative 3x squared divided by x squared would give me negative 3. And while I don't get it to completely divide out, at least it does reduce a little bit with the 10x. The 10x over x squared would be 10 over x. Okay, is that all right? Okay, so if we're thinking about this from the perspective of finding limits now, because that's what we're supposed to be finding, it says it wants to find the limit as x approaches infinity. So I want the limit as x approaches infinity, and I can use that function's simplification version that I just did. So 5x minus 3 plus 10 over x. And this piece at the end fits the description on the previous slide, right? It goes to 0, right? Because it's x to the 1 as the rational exponent on x. So this piece actually will go to 0, so that works out just fine. However, the first pieces do not. What happens if you have a value that is getting increasingly larger, right? X is getting increasingly larger and it's being multiplied by 5. What number is it tending toward, or what value is it tending toward? Who said what?
Infinity.
Say it louder.
Infinity.
Infinity, right? If x is going to infinity, then 5 times something that's going to infinity is also going to infinity. So I can't plug in infinity. If you write 5 times infinity, you're going to get points taken off because that's absolutely incorrect. There's no such thing as 5 times infinity. However, conceptually, that's how we're thinking about it. X is becoming infinitely large, so 5x is doing so as well, right? So this value, in a very much the same way that the ending value goes towards 0, goes towards infinity. Agreed? What happens to the 3 in the middle? Well, it's constant, and it just stays at negative 3. It doesn't do anything very exciting. But what happens when we have something infinite? We subtract off 3 and we add 0. It's still infinite, right? That is still an infinite quantity. So this limit is infinity. Or we could actually say the limit doesn't exist, more specifically, but it doesn't exist because it's going towards infinity, right? We've talked about the fact, this is way early on, right? Chapter 2 stuff. We talked about the fact that things are going to infinity. Was it 2? Chapter 1. Now I can't remember. Chapter 1, wasn't it? Chapter 1. We talked about things being not defined, right? Infinity is not a number, right? Limits are supposed to be numbers. But by saying that the limit is infinity, it really tells us how it fails to exist. It fails to exist because it's becoming infinitely large. as opposed to something like a sine graph where it's oscillating. That fails to exist because it oscillates, right? So when we're saying that it's equal to infinity, we're really saying it doesn't exist because it's becoming infinitely large. All right? Is that good? Okay, we're going to change the direction slightly. We still have the same function on top, but on part B, we're going to be dividing it by x cubed instead of x squared. So we're going to go through the same process. We're going to have 5x cubed minus 3x squared plus 10x, and now we're dividing it by x cubed. So how will this simplify?
5 minus 3 over x plus 10 over x squared.
Okay, excellent. Does that make sense to everybody? Wonderful. And then we're going to use that version to take the limit as x goes to infinity. Okay, so what happens to the 5? It's constant, it just stays, right? What happens to the 3 over x? That goes to 0, right? How about the 10 over x squared? It also goes to 0, yeah? Anything over x with a power that is positive and rational is going to go to 0. So I have something that's going to have a constant, minus 0, minus 0. What's the limit? 5. And if you think about this from a college algebra perspective, what we did in college algebra is we considered again the exponents, and these exponents now match. The highest degree on top, the highest degree on bottom, and match. And so what we did in college algebra is we looked at the ratio of the leading coefficients, and that's an understood 1 down there. So the ratio of 5 on top to the 1 on bottom gives me the same 5 from an algebra perspective instead of from a limits or calculus perspective. Is that all right? Okay, so we're going to change up some different functions now that we've kind of dealt with the two kind of extremes of what can happen, where we get infinite, get something infinite, or we get something finite. All right, so we're going to find the limit, if possible, in each of the scenarios, but I want you to take a look that on these, we don't have the ability to simplify the algebra quite so friendly, because the denominator has addition or subtraction in it, right? Yeah, so there's no just dividing the numerator by pieces of the denominator. That's not a thing that we can do here because the denominator has more than one term. So we have to approach this from a slightly different perspective, though I believe it's a perspective we've seen before. If not, that's okay. My classes are starting to run together at this point, so I apologize if I'm telling you something and you're like, she didn't know what she's talking about. Apologize. Okay, so from algebra, take a look at the exponents. What's the highest degree exponent on top? 1, and the highest degree exponent on bottom is 3. And in algebra, when that happened, that the highest degree on top is smaller than the highest degree on bottom, the limit's 0. So we are going to expect that this limit should be 0 from algebra, okay? So let's look at it from a limit perspective and decide why that's the case. So what we're going to do is we're going to find our highest degree exponent, that's a 3, and we're going to multiply the numerator and the denominator by 1 over x cubed. Have we done this before? No. Okay, so it was my other class. No problem. Okay, whatever the highest degree exponent is, that's what you're going to use. And what we're going to do is we're going to distribute that through each of the pieces. Okay? And just like we did, I know we did this before, anytime we're doing a limit and we actually haven't found the limit yet, we're going to write the limit part again. So limit x goes to infinity. So 3 times 1 over x cubed is 3 over x cubed. How about the negative 2x times the 1 over x cubed? I'll start negative. 2 over x squared. Okay, is that all right? I'm going to simplify as we go. 2 over x squared. On bottom, the 3x cubed times the 1 over x cubed would just give me 3, right? And then the last piece is a 1, so I have minus 1 over x cubed. Now, one of our limit processes that we had back in chapter 1 said, if I have lots of little pieces of limits along the way, and I used this over here on these problems too, I just didn't mention it. Instead of worrying about the composite, the entire thing, I can look at the limit of each individual piece. So we're not going to have to separate that and write it that way. I mean, I could do that. I think that seems a little bit unnecessary. I don't want you to have to write out the limit as x approaches infinity of 3 over x cubed minus the limit as x approaches infinity of 2 over x squared divided by, we all said thank you, right? You don't want to do that, do you? No. Okay, we have a property of limits that does not force us to have to do this all together, but to think about them each individually. The reason that's nice is because, again, I can think about each one of these pieces and consider what their specific limits are. So what's the limit of 3 over x cubed as x goes to infinity? That's 0. How about the next one? Also 0. How about my 3? It's just 3. I'll write it underneath. And how about the 1 over x cubed? 0. So what I truly have, right, me evaluating each one of those and deciding 0, 3, infinity, whatever they are, is me taking the limit. That's what I'm doing, which means now on top I have 0 minus 0 over 3 minus 0, and all of that is 0. So I don't care whether you write this particular step. You could jump over that if you wish. But does that make sense? All right? So we're changing each of the pieces into something that we have a theorem that tells us what to do with it. Okay, let's try another one. Now this one's a little bit different. It's a little bit different because I have a square root, right? Now, you should recognize when you look at that denominator that x squared minus x, like the dominant piece, is the x squared, right? X squared is going to get bigger much faster than the x's. So if I were to take x squared and I were to take x and let them both go to infinity, x squared is going to take over eventually, and the denominator is going to become infinitely large. Does that make sense? The power dominates. Okay, so what I really have in terms of what's really going on here is I really have something far enough along the way that looks more like this. It'll have the same limit. And if I were to take the square root of x squared in the denominator, what would I have? I'd have x. So I really have x on the bottom and x on the top. And from a rational exponents perspective from college algebra, this limit should be 1 over 1. I should get a limit of 1 here. That's what I'm expecting to have happen because the coefficients of both are the same and the exponents are both the same. Okay? And you might be like, well, how can you just disappear the negative x? Well, you can't. But it gives you a perspective of what you're expecting to have happen in the long run, right? Like if you put x over square root of x squared minus x in your calculator as y1, and in your calculator in y2, you put x over x, or just 1, what you would find is if you scrolled far enough to the right, they'll become infinitely close together. Okay? That's our perspective of what we're doing. We're trying to see, as we go to infinity, what's really going to happen here. It also helps us to decide what we're going to multiply by. Over here, it was very obvious. I looked at the highest degree exponent. It was 3, so I multiplied by 1 over x cubed, right? It was very obvious. Here, not so obvious because I've got the radical involved. But what I really have is the square root of x squared, which is the same thing as x, so I really have x to the 1. So here's what it looks like. I multiply the top and the bottom by 1 over x. Now the top is fine. Nothing alarming there, it's just 1. But the bottom, in order to input this inside of the square root, I have to have it under a square root as well. Well, if I put it under a square root, how am I going to accommodate for the fact that I just threw a square root in there? Well, I'm going to square the x. The square root of x squared is the same as x. So I have the square root of 1 over x squared, and I'm arguing that this is equal to 1 over x. Do you agree? So if I stick the square root on, I can stick the squared on, and then I've compensated appropriately for it. The reason that that matters is because, again, in algebra, we're told that if we had something like this, the square root of x times the square root of x, right, they're both square roots, I can merge them both underneath the same square root like this. Yes? So So I need this second piece that I changed right over here that says the square root of 1 over x squared now to be underneath a radical in order to combine the two radicals together. Can't do it without them. So once I've put that in there, I now have the ability to multiply my x squared times 1 over x squared here and my negative x times 1 over x squared. That's what it takes with the properties that I have. So I can clean up what's underneath the denominator now, and underneath the radical as well, for that matter. I have 1 on top, and then this is the square root of 1. And then what do I get for the second piece? 1 over x. Okay, but again, limits, back in chapter 1, says I can evaluate each of these individually. Well, everything that's a constant stays. I don't really have to evaluate it, right? Like we did it over here, but I just wrote the 3 again. It wasn't very exciting. And you can write all the 1s again if you wish, but they're not going to change either. So the only place that I have a variable right here is this one. And what is the limit as x goes to infinity of 1 over x? 0. So on this one, I get 1 on top, and I get the square root of 1 minus 0 on bottom, and that gives me a total of 1, just like we expected to have happen, using limits and some properties along the way about radicals, of course, too. Okay, is that all right? This square root process trips people up a lot, so make sure if you have any questions, you're asking me. Yeah?
What if you just put x squared minus x, like that radical, you put it in parentheses, then to the 1/2, and distribute it to 1/2 at the very beginning?
Yeah, so I think here's what you're asking me. I think you're saying if I rewrite this, I'm just looking at the denominator, like this, am I able to distribute the 1/2 like that? Okay, so let me answer the question in a slightly different version. Is a squared plus b squared square root equal to a plus b? Do you know? Try some numbers. We're going to try numbers that you're familiar with. What's 3 squared plus 4 squared? 25. And the square root of 25 is not 7, right? So we don't have a distributive property for exponents like we sort of sometimes expect to have happen, like we do with multiplication. There isn't a distributive property for that. So this fails to work, which by the same token would mean that fails to work because it's just an exponent that looks like a 1/2 instead of a 2 or whatever. Yeah, we can't distribute the 1/2, unfortunately. Okay, any other questions? But I always have people try. Trust me, always. Okay, I think there's one more on this one. Trig function. Okay. So I mentioned trig functions earlier. They oscillate, right? And so they have this sort of a weird behavior kind of thing. They don't just necessarily go to infinity, some other stuff happens. So there is kind of a trick to trig functions. Now, one of the things you do know about trig functions is that they're bounded. Bounded means that they have a value beyond which they do not extend, right? They're bounded between -1 below and +1 above, unless they have a coefficient, and that affects it, of course, too. But a trig function, sine x, cosine x, those are the ones I'm talking about, are bounded between -1 and 1, right? Okay, so what we're going to take a look at is something called the squeeze theorem. All right, so we're going to notice that, I'll write it this way, that -1 is less than or equal to the sine of 2x. The 2 inside does not affect the boundingness. It affects the period, how quickly it repeats and oscillates, okay? But this is bounded between -1 and 1. Yes? Yes. Okay. My limit as x approaches infinity means that my x values are positive. Yes? So I can actually take each of these pieces of this inequality and divide by x, and it will keep or preserve the direction of the inequality. Okay? If I were dividing by negatives, it would switch the direction of the inequality. Not. I'm dividing by something that's positive, so the direction of the inequality stays the same. So far, so good? Okay. Now, that's not quite what my question asked. My question asked about limits. So now I'm going to insert the limit into each of the three pieces of this triple inequality. So this is the limit as x goes to infinity of negative 1 over x on the left, the limit as x goes to infinity of sine of 2x over x in the middle, and the limit as x goes to infinity of 1 over x on the right. Okay, are we good? Okay, these outer pieces of my inequality, we know how to do. Yeah? Do I have x? Yeah, I do. Okay, just checking. What's the limit on the left-hand side of 1 over x?
0.
It's 0. What's the limit on the right-hand side of 1 over x? Also 0. So if I am sandwiching something in between 0, it has to be greater than 0, and 0 that has to be bigger than 0, right? Like it has to be in between the two, both bigger and smaller than 0. It must mean that the thing in between is also 0. There's no room. There's no room for it to be anything else, right? This limit is still sandwiched, hence the name of the sandwich or the squeeze theorem. You hear it called both, the sandwich theorem or the squeeze theorem. It is in between. So the limit as x approaches infinity of the sine of 2x over x is equal to 0. Isn't that clever? We turned a trig function into something in rational form that we already could do.